We're going to... Oh.
Okay.
Yeah, I think so. So we're going to hear Irmak Saglam talk about fair omega regular games.
Thank you. Okay. So okay, let's start with games for verification. As I have mentioned, I will start by giving some motivation. So why do we use game for verification? Yes, works. So two-player games played on finite graphs come from correct by design synthesis of cyber-physical systems. So they are used in verification and synthesis. And let's dive in with an example. Let's say we have a robot hand and we have a pile of blocks on a table. And whenever the robot moves, it tries to remove a block from the table. And let's say this robot is perfect. That is, whenever it tries to move a block, it achieves to do so. Then we can model this process as a finite game, actually one-player game. And the circle nodes are controlled by the robot. The labels on the nodes represent how many blocks are left. And the moves of the robot is the outgoing edges of the nodes. So let's say our aim is to clean the table. Then we can represent this objective as a reachability objective to the node with label 0. If we ask the problem whether the robot hand can win this game or equivalently achieve the objective, then we get a positive answer because it's perfect, so after n many steps, the table will be clean. However, life is not usually as perfect, and robot hands are not perfect, and when they try to remove a block, they may fail to do so due to environmental uncertainty. And typically, we model this environmental uncertainty with a second player. And here we will show this with the square player. And as you can see, whenever the robot hand tries to remove a block, it goes to an environment node, a square node. And the square node either lets it pass to the next node, or it sends it back. So if it lets it pass, it means that it lets it move the block. If not, then it makes it fail. Then we can ask the question again. Can the robot win this game? Can it clean the table? Now we get a negative answer, because the environment can always make it fail. However, this is also not exactly what we want either. We want a more realistic scenario. We don't want, life is not as perfect, but it's not always purely adversarial either. So this brings us to games for verification, but under some assumptions. So to get the right level of abstraction is hard, and we don't want to over-approximate environmental uncertainty. And one tool we use for this is called environment assumptions. And these assumptions are something that we assume environment satisfies, and we ask the question whether we can win the game, given that the environment satisfies these assumptions. And as you can see, some of the edges have turned into dashed edges, and these will carry the environment assumptions. So we will say, we assume that whenever a square player node is visited infinitely often, it will eventually let progress through its dashed edges. Then we ask the question again. Given that the environment satisfies this assumption, can the robot hand clean the table? Now we get a positive answer, because the robot hand will constantly try to remove a block, but eventually the environment will let it achieve it, and after finitely many steps, it will clean the table. So I talked about all these for motivational purposes, and throughout this talk, we will talk some canonical games for verification called parity games, which is actually a generalization of the reachability games I've just implicitly presented. Then we will talk about parity games under some assumptions that are just like the ones that I have just presented, but we will put these assumptions on both of the players. Not studied before. We will tackle some problems there, and we will try to solve them by giving what we call a natural framework to treat such games. And we will give an algorithm to turn these games into normal parity games with only a polynomial size increase, which means that we will give an efficient way to solve these games, because parity games can be solved rather efficiently. So, yes. Then let's start with parity games. We have a finite game graph, which has no dead ends. The nodes are divided between two players, circle player and the square player. And the play is just a trajectory drawn by a token being shifted through the edges by the owner of each node. And an example is display pi that starts from V1. Now the square player can either decide to take the self loop or take the edges to V2 or V3. Let's say it takes it to V2. Then now the circle player decides what to do next. Let's say it takes the self loop for one step, then takes it to V3, then to V4, and from there on, square player leaves it at V4. So this is a play. And in parity games, the parity winning condition decides who wins a play. So the parity winning condition is given by a labeling of all the nodes with some natural numbers, which are also called priorities of these nodes. And the parity winning condition asserts that the circle player wins a play if and only if the maximum priority seen infinitely often in the play is even. So this means that we just get a play, we look at the nodes that are visited infinitely often, then we look at the priorities of each one of them, and we look at the maximum of these. If this is even, then the circle player wins, and if this is odd, then the square player wins. And that's why we also call these games players even and odd players sometimes. And if you look at this play that we have just constructed, the only node visited infinitely often is V4. So the maximum priority seen infinitely often will be 3, and therefore the odd player or the square player will win this play. And now let's look at a strategy. So our strategy is a behavior of one of the players. Let's say the circle player. Let's say the circle player only takes the green edges in this game, no matter what the square player does. So whenever a play comes to V2, it shifts it to V1. Whenever it comes to V3, it shifts it to V1. And under this strategy, no matter what the square player does, the circle player will win this game from V1, V2, and V3. And that's because, let's look at, so V1, what can the square player do? It will either take the self loop, but then it will always see the priority 4, but this is even. It wants to see an odd priority, so it can shift it to V2, but then it will be shifted back, or V3, but then it will be shifted back. So no matter what the square player does, all these plays will see the priority 4 infinitely often, and since this is the maximum priority, even will always win these games. So, however, from here, for example, the square player can take the self loop, and circle player cannot do anything, and the square player wins with this strategy from V4. And so this is called the winning strategy for circle player from here. And in fact, parity games are determined, meaning that each of these nodes have exactly one winner. From each of these nodes, exactly one node has a winning strategy. And when we mention solving a parity game, what we mean is just finding this sets, the winning regions of the players. And let's come to square fair parity games. On these games, we have a parity game. Now we will put this assumption that I have just mentioned in the beginning to only one of these players, and in this case, the square player. So we have a parity game, and we have a subset of its edges called the live edges. But the source nodes of all these live edges belong to the square player. So it means that the assumption is inflected on the square player. So on this example, we have turned some of the edges to the live edges, which are shown by red and dashed lines. And the play is called fair. You don't have to read. If and only if the following holds. For all of these dashed edges, if the source vertex of the edge is visited infinitely often in a play, then the dashed edge is also taken infinitely often. So an example is, let's look at this play that whenever the play V1 takes its self loop and the edge to V2 alternatingly, and V2 always sends it back. So this just draws the play, starts from V1, then the self loop, V1 again, then this edge V2, then V1, V1 again, V2, V1, V1 again, and so on. So this is a fair play because source node of a live edge visited infinitely often is V1, and the edge is also taken infinitely often. So this is fair. Just an example. And in these games, it is harder for the square player to win because it has assumptions. So in order to win, it must both obey the fairness condition and satisfy the parity condition that the square player wins if and only if pi is fair and the maximum priority seen infinitely often is odd. So if we look at this play, it is fair. However, the maximum priority is 4, so this will be won by the circle player. And let's look at another play that only takes the self loop in V4. Now this is not a fair play anymore because the source node of a live edge is taken infinitely often, but the live edge itself is not taken. Then it's again won by the circle player. So, square fair games are also determined that is each node has exactly one winner, and in fact, since even is stronger here, all the region is won by even. And one can turn a square fair parity game into a normal parity game with only a linear increase in the size. And this is due to a result of Chatterjee, Jurinsky, and Hensinger from Chi. And I will just briefly give the gadget, but not try to really explain it too much. So we have a square fair parity game, and 2k is the maximum priority on its nodes. We can replace each square node that has some live outgoing edge with the following gadget. Okay, let's say this is our square node, and it has some live outgoing edges. And let's say ELV is its successors, which it goes to with some live edges, and EV is all our successors. Then we just take this out of the game and replace it with this confusing 3-step gadget. So this, what this does is, magically, it turns it into a parity game. And I will not give full intuition, but I want to just grab your attention onto some points. So we have the same node, so the priority of this node and this node stays the same. And now the square player gives the right to choose to some circle, one of k circle nodes. And now this circle node, ignore this is not used normally, but decides to choose between a square player and a circle player node. And remember, the square player wants odd to win, but this needs to pay an even punishment in order to be able to choose the next move. And vice versa for the circle player. So this does the magic, but let's not go into it. And so the square nodes can go to all of the successors of V, and the circle nodes can go to the dashed lines, which just forces V to take its edges infinitely often and gives the right to choose to circle, etc. But what I really want to emphasize is this rightmost branch. So this is the most important branch, because this determines how we will treat in the unfair games. Because as you can see, so this just goes to a circle node, but this is kind of redundant, right? Circle cannot choose anything. So this just goes from here to a square node, and this gets to choose its successor. However, this is not really, here it's not allowed to choose its successor, because if this is seen infinitely often, it has to take its dashed edges infinitely often. If it doesn't do so, then it loses. But it seems like in the parity game, it can choose its successor all the time by taking the leftmost edge. However, if it does so, then it pays the price of 2k infinitely often. And 2k is the maximum priority in the game, and it is even, so this will make it lose. So it's not an option for V to take its leftmost edge, because if it chooses to do so and play unfairly, then it will lose due to the high even punishment. This is just I wanted to emphasize, because we will generalize this notion. So just to show how it turns into a parity game, let's take the parity game from previously. So the nodes that don't have any live outgoing edges stay the same, V2 and V3, and their outgoing edges also stay the same. And we replace V1 and V4 with these 3-step gadgets. Their priorities stay the same, the gadgets are the same, and yeah, these just are the normal successor and live successors of each node. So we will just connect these to the respective stuff, and this is the ending parity game. These two games are equivalent, meaning that whoever wins a node in the square fair parity game also wins the node in the parity game. This was all won by even, so this is all won by even. Okay, now, this brings us to what we did. We have generalized these assumptions to both of the players. So now, again, we have a parity game, and we have live edges, but the change is that now the source vertices of the live edges do not have to belong to the square player, it can belong to any player. And in fact, we have two live edges on this example. One stems from a circle node, and one stems from a square node. And now, intuitively, if both of the players play fairly, we want the parity condition to decide. And if one of the players play fairly and the other unfairly, then we want to make the fair playing player win. So, however, this leaves something open. What if both of them play unfairly? So now let us look at these regions. So this node is won by even, because any play that ends here does not see a live vertex infinitely often, so it is trivially fair play, and the parity condition decides who wins, and it's 2, so even player wins, and on the other hand, the odd player wins. But let us look at, for example, V2. So V2 is a circle player node. If it takes its live edge, then it will go to an odd winning region and lose. So it always wants to go to V3. And similarly, V3, if he goes to V4, then he will lose, so he will always go to V2. Then they will have a V2, V3 cycle, which is an unfair cycle, unfair for both of them, but then who wins this cycle? So there's no natural winner, and we need to somehow determinize these games to be able to solve them. And so we determinize them by what we think is a natural framework. So we use 2 different parity conditions, alpha and beta. So this means that our game has 2 different labelings. Let's say the first labeling is the alpha labeling and the second is the beta. Now, a general winning condition for a play pi says if one of the players is fair and the other one is unfair, then the fair player wins for both of the players. And if both of them are fair, then the winner will be determined according to the alpha player, which is the same as before. And if a play is unfair for both of them, then it will be won according to the parity condition beta, so the second labeling. And if you look at the second labeling, in the cycle V2, V3 cycle, the maximum priority sin will be 4, so this will be in the winning region of the even player. So this is the framework, and we will call such games fair alpha beta games. So now how to solve them? Let us first look at the subclasses where beta is trivial. Let's say beta is bottom. Then this means that mutually unfair games are won by the square player. Then this will be won by the odd player. And actually, we can turn these games into a parity game using the gadgets very much like the square fair parity games. Just remember that if we had a square fair parity game with the maximum label 2k, then we could just replace it with this gadget. For an alpha bottom game with maximum label 2k, for the square nodes that have live, we will take the same gadget. For the circle ones, we will take the dual of the gadget, and we will add one more label, 2k plus 1. This intuitively what it does is as follows. So if the square node decides to play unfairly, then it will force the game to see priority 2k. And if the circle decides to play unfairly, it needs to see priority 2k plus 1. So if both of them play unfairly, the play will see priority 2k plus 1 infinitely often, and since this is an odd priority and the maximum priority in the game, this will be won by the square player. And similarly, if we have an alpha top game, this means that the mutually unfair plays are won by the circle player. We just add one more label to this gadget, 2k plus 2, and this forces the mutually unfair plays to see the priority 2k plus 2 infinitely often and makes them be won by the circle player. And how to solve fair alpha beta games, I will just briefly mention. We will use very similar gadgets. Now, each node in the parity game has to carry 2 memory values. One is, let's call splash. This is either the circle or the square. And this carries the value of which player played unfairly last. And this p beta will carry the value of the beta priority sin, maximum beta priority sin infinitely often. So whenever we switch edges, we will just carry the maximum beta priority with this memory node. And so all of these edges will just carry this priority, but one edge. And this is the rightmost edge of this gadget, it could also be that gadget. It was just a choice. We need to do it at one place. So this nodes, if splash is a circle, this just keeps on carrying the alpha priority. If it is square, this switches to beta priority, which means that this node will be activated infinitely often if and only if both of the players play unfairly infinitely often. And then this game will be dominated by the beta priority. But if not, if both of the players don't take their leftmost edge infinitely often, then this will not be activated infinitely often, and therefore we will just win according to the alpha priorities. I'm sorry for this very brief introduction. This is just a supporter for this. And with that, I leave you with a contribution. So we introduce a framework to express meaningful winning conditions for parity games with double fairness conditions. We call these games fair alpha beta games. We give an algorithm to turn a fair alpha beta game into a parity game. And if beta is trivial, this will only cause a linear size explosion in the parity games, and actually this much. And in general, the conversion increases the size polynomially, actually this much. And this gives us that fair alpha beta games can be solved in quasi-polynomial time because parity games can be solved in quasi-polynomial time. And we additionally give fixed point algorithms to solve these games on the original graph and save space, but I didn't mention that. And thank you very much.
Questions?
Yeah, thanks for the talk. I was just wondering, in the game, because when we have a fairness condition for both players, it seems that you decide, so couldn't you just say, so what happens if you say that, unfair plays are just disallowed? You cannot have an unfair, like a strategy that has unfair plays.
Then this would limit the shapes of the games that we can consider. Then we should analyze whether this game actually has any undetermined nodes according to unfair plays. Yeah.
I have a question about the link with new calculus and there's parity games a strong connection with in the new calculus you can also state fairness properties.
You cannot what?
We can also state
we cannot state?
And I was wondering if it's possible so to see like the new calculus as a way a government framework to state both as, I mean, it's possible to translate this kind of fairness parity games in the new calculus.
This is actually what we do in the part that I didn't show, that we write these as fixed point formulas in the mu calculus.
Okay.
And yes, so this fairness condition is a special one actually. In general, I mean, if we consider general fairness, then we can encode them as street conditions, which is again, yes, can be expressible in mu calculus. But these are very easy fairness conditions somehow that you can capture with small gadgets like we have shown. Something like this, yes. Thank you a lot.